This is the second lecture for Algebra-Based Physics 220. It will be about what are called the kinematic quantities, the quantities that describe the motion of objects. And these are vector quantities, so this will be an application of the vector techniques that we learned in the previous lecture. So just a quick overview of what we'll see. We'll talk about mechanics. Mechanics is the subject of this course. The second semester of the first year physics course is basically electricity and magnetism, but here we talk about the motion of objects. And in particular today, we're talking about kinematics, which is something that has to precede the discussion of dynamics, and I'll tell you what that means in a few minutes. I'll quickly give the definitions of the kinematic quantities, and then we'll use them in order to describe the motion of an object. And through that process, we'll sort of introduce all of these concepts: the path, the position, the displacement of an object, then quantities related to the velocity of an object, and finally the acceleration of an object, and show how they're all related, and in particular how you use them in terms as they are vectors. So we'll be doing vector math with them. I'll do an example to show you how we use this in practice. And then we'll talk about how these things are related: position, velocity, and acceleration, the three kinematic quantities, and show how you can analyze one-dimensional motion through graphs. To start, let me just give you a little bit of an overview of the course. We're going to talk about classical mechanics, which is the science that was developed by Newton to describe things like the motion of balls falling off of buildings or the motion of planets going around suns. Basically, it's the description of all motion of objects. And what we'll be concerned with primarily in this course is the motion of a particle. So Newton's second law, which is the main law that describes motion, tells you how the motion of a particle is determined by the forces on that particle. You can build up larger objects by putting particles together, but basically, especially in the beginning of this course, we'll think of every object as just being a point in space, a particle. So in some cases, particle motion is sort of obvious, like if you talk about a ball that's being hit off of a bat and it might take some path that looks like this, then, well, a ball is not much more than a particle, and we can talk about the velocity of that small object. But sometimes we'll talk about things like a box that's going down a ramp. Maybe this is the velocity of that box. That box we'll consider to be a particle. So it'll just be, you just think about it as a dot in space. And then there are things that are almost ridiculous to think of as particles, like a car, but in the same case, we'll consider it as a point in space, a point that moves through space, and also, when we get to dynamics, a point that has forces acting on it. So the complete description of motion is governed by Newton's three laws of motion. The most important of them is called Newton's second law, and you might have heard of it. It's F is equal to ma. It's actually, first of all, a vector equation. So each side has a vector sign over it. And it's not just any F, it's the sum of all forces on the object of mass m. And the sum of all forces equals the mass times the acceleration of the object of mass m. Now, when we get to Newton's second laws, we'll see that forces, which you may not know already, are basically defined through the laws. So the three laws will give you a definition of what we mean by force. And the same goes for mass. So we'll have some way of understanding what mass is just through the laws themselves. That's called an axiomatic theory, where it provides all the information you need. But the acceleration is something that we need to know before we start using Newton's second law. And that is part of kinematics. It's part of the description of motion. And in fact, it's basically what Newton had to invent in order to write down his laws. He had to invent kinematics, and in particular the calculus of kinematics. Calculus is a field in mathematics which we won't really use explicitly because you weren't required to take that prior to this course, but implicitly it's sort of everywhere in Newton's laws, and we'll see how that works today. So Newton's laws describe the motion of objects, and that field is called dynamics. The dynamics is an explanation of why things move. And spoiler alert, this is the answer. Objects have an acceleration if they are acted on by forces. But as I said, we need to understand what A is before we can even use this equation, and that's what we'll be doing today. So before we get to Newton's second law, before we get to dynamics, we have to get to kinematics, which is, one could state it as how things move, simply describing precisely how things move through three-dimensional space. And the parts of that are position, velocity, and acceleration. So let's look at their definitions. So position, we write usually with the variable r, and as all of these things, it is a vector quantity. So let's write vector here. So don't ever forget that we're talking about vectors. These are not just numbers. They are in two dimensions. They're pairs of numbers. They have a direction and a magnitude. So this is the position vector, and just like any vector, we could think about it if we choose some coordinate system, as we talked about last time with vectors, then this will take on, for example, three components in three-dimensional space, r sub x, r sub y, r sub z. Although for the position vector in particular, we usually don't write it like that. We usually just say x, y, and z, meaning if you have a coordinate system here, x and y, then a particle moving through that coordinate system is described by a vector r, and it will have components r sub x, which we just call x, and r sub y, which we just call the y position of it. So you can see that this particular particle is moving sort of down in y. It's about to reach the minimum y value, and it's moving rightward in x. So the y value will be going down, the x value is getting larger, as you would see. And we'll consider that in more detail in a moment. So that's the position. The next thing that we need to define related to the position is called the displacement. And the displacement is written as delta r, and it corresponds to the change in position over some time interval. So we might say that this is displacement over the time interval from t initial to t final. So what is delta r? Well, it is the difference r at t final minus r at t initial. And we could write that as, well, we could write it as delta rx, delta ry, delta rz, but we could also just write it as delta x, delta y, delta z. So if we go back up here to our picture, if we chose another moment in time, there would be a different position vector that went to that point, and the delta r vector gives us the change in position from one to the next. And we'll show how we construct that from this definition here. Remember, these are vectors, so this is a vector equation. This is a subtraction of vectors, which we either need to do with graphical addition of vectors or with finding components and subtracting the components in x, y, and z separately. We'll do that. Next we get to velocity. And velocity comes after position because it depends on position. So the definition of the so-called average velocity, this symbol means defined as. So a colon with an equal sign, it means defined as. And the definition of average velocity is the displacement divided by the time interval, the length of time. So that means that it's also corresponds to a time interval. So this is the average velocity over the time interval ti to t final, t initial to t final. And what we mean by delta r, well, we already said that last time. It's r at t final, not last time, but just above. It's the vector r at t final minus the position vector at t initial. And then delta t is just a number. It means t final minus t initial. So that is what we call the average velocity. And we'll see in a moment why that will correspond to what you might think intuitively about what you know about velocity already. The average velocity is different than the velocity, the so-called velocity. The so-called velocity is also sometimes called the instantaneous velocity at a time t. So average velocity, by its definition, corresponds to a time interval. You have to pick 2 moments in time and find the average velocity over that time interval. For velocity, it corresponds to a single moment in time. But the way that you get it, as we'll see, is that you take the average velocity and you allow the delta t to get smaller and smaller. So it's the limit of the average velocity of delta r over delta t as delta t gets very, very small. So basically you calculate an average velocity over some time interval, and then you make that interval smaller and smaller and smaller, and that becomes the velocity at the moment in time that you reach when that interval gets very small. And we'll see that graphically in a moment. Finally, we have the acceleration. So the velocity depended on the position of the particle. In the same way, the acceleration depends on the velocity of the particle. So the definition of the average acceleration is the change in velocity of the particle, vector, over the change in time. You see how these are sort of symmetric here. So velocity is the change in position over time, acceleration is the change in velocity over time. And that relationship will become very clear by the end of the lecture today. So what does that mean? It just means, again, delta v is v at the final time minus v at the initial time. And I'm missing something here. It's a difference of vectors. So it's not just 2 numbers subtracted. And then this means t final minus t initial again. One thing that we could say here, and we'll come back to this, is that you can see that the acceleration vector is an arrow that points in some direction, and it will be pointing exactly in the direction of delta v. Whatever the delta v vector is doing, that's the way the acceleration points. And that's because delta t is just a number. In particular, it's always a positive number because we assume that the final time is greater than the initial. So all that number does to this vector is sort of lengthen it or shorten it. The direction doesn't change at all, so that means acceleration points in the direction of delta v. That was average acceleration, and acceleration, or instantaneous acceleration, again at a moment in time, is defined in the same way. You take the average acceleration and you allow the time interval to get very, very small. So that's delta v over delta t. This looks like some sort of technical mathematical language, and it is. This is from calculus, and it's actually called the derivative of the velocity function. You don't have to know about that, and you don't have to know really what this technical mathematical language means, except that you're going to see that it's very clear when you look at it graphically what it means. And you'll see that in the next section. So let's use those quantities. Let's use the kinematic quantities to try and understand how we would observe and precisely describe the motion of an object. So I'm going to use a bird flying through the air as our example. And here you are standing below. We could give you like a stopwatch and a meter stick or a laser to try and measure some distances maybe. Let's give you a stopwatch there. And you're going to try and describe how this object is moving. So let's try and do it. So the first thing was the position. And the position is, well, actually, sorry. The first thing actually is this dotted line. So this dotted line is the sequence of all positions of the bird, and we call this the path of the object. So it's a path through a three-dimensional space that the object takes. This bird, because it has its own volition, it can go wherever it wants, and it makes this really this curvy path, which we'll describe. We'll often consider things that move much more regularly, like something that moves on a circle or something that follows the parabolic path of a falling object. But just in general, an object could take any path through three-dimensional space, and it is called the path. So what is position? Well, position requires that we define a coordinate system first. And that coordinate system is completely arbitrary, so you can make a selection of whatever coordinate system you want. I guess I'll put mine over here. So I'll draw my coordinate systems in red in general. And let's just use this as a standard coordinate system. So this is just the conventional way of drawing a coordinate system, where we draw x horizontally and y vertically. Maybe I should make the y one a little bit longer so that we can actually get it to go past the object. And maybe I'll do the same for the x. So here's our x direction. So that is our coordinate system of choice, and you could choose any one you want, but that's the one I chose. The position is defined to be the vector that goes from the origin of the coordinate system to the object. So our object is a bird, but remember we consider it to be a particle. So let's just put a point there. And that means that we have a vector that goes directly to that point. Draw it like this. And that's what we call the r vector. We might call it actually the r of t vector, meaning it's the position at this one particular moment in time that we're looking at. That's the position. Now, we could let the bird go, and maybe in a few minutes later, maybe a few seconds later, the bird will be over here. So at some later moment, we would have a different position vector. So now you can see, so if that was r of t initial, then this is r of t final here, over some interval from t initial to t final. So that's the position of the object. Let's copy that over so we can put it on another. Oh dear, I copied my bird. Okay, there it is. Our bird is getting wider. What I was going to say back here that I forgot was, you can see now that the position vectors are hitting the path everywhere, and that's what I meant by the path being the sequence of positions, right? So as time moves forward in time, these vectors move to different points along the path and give us the different positions. Now we want to look at displacement. So remember how we defined displacement. Displacement was delta r, which is r at the final time vector minus r at the initial time vector. So what we can do is we can put that down here. We can do graphical addition to try and figure out exactly what it is in this case. So this thing here means r at t final vector plus the minus r at t initial vector. And we know how to add vectors. So the minus sign, remember, just flips something around. So let's try that out. So let me grab these vectors. Oops, I grabbed the axis as well. Don't need any of that. So there's our t initial, our r of t initial and our r of t final. And now let's do graphical addition. So let's start with a coordinate system. I think I probably need a little bit more space here. So let's start with a coordinate system. And then from our equation, we see that we take r of t final first. And we'll place its tail at the origin. And then we add to it not r of t initial, but the opposite of that vector. So we want to take r at t initial, but with a minus sign in front of it. So let's do that. There it is. And remember, the resultant, the sum of those two vectors, goes from the beginning to the end, from the origin to the last head. So this is our resultant, and the name of that is the delta r vector. That's our delta r. So what is that back on our picture? Well, let's copy it over. Remember, I can slide a vector as long as I don't rotate or lengthen it. And you see that that delta r vector goes from the initial point to the final point. That's what we mean by it. So the displacement is a vector that points from the initial position to the final position. What's nice about a displacement is, although my positions were completely determined by the choice of coordinate system that I made, the displacement does not depend on that. So you could imagine, let me just sketch this and then I'll erase it because it's going to be ugly. We could have put a coordinate system up there. We could have had an R1 and an R2 like this, and we would have found exactly the same displacement vector when we did that graphical addition. So the displacement no longer depends on this personal choice of coordinate system that you made. And that's nice because we don't want physics to depend on some choice that the physicist makes when doing the experiment or the observation. So it won't. Okay, so that's our displacement. Let's look for a moment at the components of the position. So let's copy this one over again. Oops. So here's our bird, and here are our two position vectors. Let's just look at one of them. So this is r of t. And the position has two components. It has the x value, that's r sub x, or we could just call it x, and it has the y value. That's y there. So you can see that as the bird is moving through space, the position vector is changing, and as that happens, the components, which are, remember, the tick marks that you get onto the axis, are then moving along the axis here. So the y is going, if we were to measure from this point here, you can see that it would start here, it would go up to here, and that was about the peak, and then it would come back down again. And here, for the x, it would start out here, project back down to x, it moves forward, and in fact it just moves forward basically all the way along there. So those are the components of the position. The components of the displacement, well, just from the definition of it, it's going to be r final minus r initial, so that's going to be just delta x comma delta y. Those are the components of the displacement for some time interval. And that would be on here, delta x, and I guess I probably should put a direction here. Delta x is getting bigger, delta y is going to be a negative number because you can see that the final position is below the initial position there. So those will be our components. Okay, so let's move on to velocity. So we had, well, first we start with average velocity. So let's look at, let me just redraw our coordinate system and our two positions. So this is our, let's just call it R initial for R at time t initial. And then we chose some other moment in time here, our final, R at time t final. What is the average velocity here? Well, the average velocity was defined to be delta r over delta t. And we already have a delta r. We found that delta r points from the initial position to the final position. Should we check if that's correct, in case I forgot? Well, based on this picture, I can see a graphical addition happening. It's not the same one that we did before. I have an r initial from starting from the origin. You add to it a delta r, and you get an r final. So let's write that equation out. I have the resultant is r final, and that's equal to the sum of r initial, starting here, added to delta r. Is that the same as our definition of the displacement vector? Well, I can subtract off r initial and I get r final vector minus r initial vector. It works, it's correct. So this is my delta r vector that we found. So what is the average velocity vector? Well, you can just see it by looking at this equation. Remember I said this is a vector equation, which means that the left-hand side is a vector and the right-hand side is exactly the same vector. So although there's a delta t here, which might change the length of the vector that you have in delta r, the direction will be exactly the same for the average velocity and for the delta r vector. So we can just draw a parallel vector that we call v average. We don't know what its length is because we weren't given any information about how much time had passed from this moment to this moment. And in fact, its length can't be measured in space here. The measurements in this picture are in meters. The measurements of a velocity are in meters per second. So in some sense, this vector lives in a different world. It lives in a different space. It lives in the world of meters per second. So the length of it we don't actually know, and in fact the length doesn't really mean anything as compared to vectors with length in meters. But we do know that it points exactly parallel to the delta r vector. Now let's consider the instantaneous velocity vector. So the instantaneous velocity comes about by saying, well, it's going to be the limit as delta t goes to 0 for delta r over delta t. It's the limit of the average velocity as delta t gets smaller and smaller. So how will that work on this picture? Well, this is our time interval delta t from here to here, and that's spanned by our displacement vector delta r. If we make the time interval smaller, then this point moves closer and closer to the initial moment in time. So we could write this equation as the limit as delta t goes to 0 as r t initial, it's rt final, but we could write t final as t initial plus delta t. And then that's subtracting off r at t initial. And then we divide by t final minus t initial. Well, that's just delta t now. So we don't have to have a t final anymore. We can just say, well, we'll just allow time to go forward a little bit more, delta t. So what does that do? Well, let's get rid of these things here. Let's leave our path up. And let's take the r final vector and bring it closer and closer. So if I bring it to here, what would happen to the resultant, in fact, let's erase our little bird. Sorry, bird, you're becoming a particle. Bird became a particle. So if our delta t gets shorter, then our new displacement vector would also be shorter here. It would point like that. Okay, what if we make our delta t even shorter? Then our final position moves to there, and our displacement vector looks like that. It's shorter. You also notice that its direction is changing slightly. Remember, the direction before went straight between these points. Now it's sort of pointing up a little bit because it's not going as far along the path. Let's take it one more. And now our displacement vector, our displacement vector now looks like this. So that's our delta r for a very small time interval. And you can see, as you take the limit, as delta t gets very, very small, as it goes to 0, this point will head to this point. And what does that mean? It means that the final delta r will point exactly tangent to the curve. So delta r will be pointing along that line. Now, of course, the delta r vector will become 0 in length at that point, but we just found that the v average also points along that line of delta r. So we know that the v average, which now becomes just v, will point exactly tangent to the curve. So if you're given an object and you're given its path, you can pick out a point on that path and you can immediately find the direction of the velocity vector, because from that argument that we just made, the velocity vector will always point tangent to the curve. So you can just, that's not a very nice tangent line, is it? So here's a tangent line. And so we know that the velocity vector will point exactly along that tangent line. We might not know what its magnitude is. We might have to be given more information, but we know that its direction points exactly along the curve. So just using this definition, basically using the definition of average velocity, allowing the time interval to get smaller and smaller, we come to some very important idea, which is that the velocity vector, the instantaneous velocity vector at a moment, the t initial in this case, points tangent to the curve. Important point. Okay, so we need to define just a couple more things about velocity before we move on to acceleration, and these are just definitions. You have to remember what they are. So we already have a definition for average velocity. That is a vector. So if you're ever asked for the average velocity, you need to return a vector in your answer. The speed is not a vector. The speed is a scalar because it's defined to be the magnitude of the velocity vector. So speed, I can say speed, which I could also write as just v, because it is, because it is defined to be the magnitude of the v vector. And we said before that if you want to write magnitude of a vector, you can write it like this, but you could also just take off the arrow and write it like this. So that's the speed. If you have components, then you know that the magnitude of a vector can be written as the square root of the sum of the squares of its components by Pythagorean theorem. We saw that last time. So speed is a number, a single number. The average speed is something completely different, and that's why I said these are definitions you just have to memorize. The average speed is defined to be the total distance traveled over the total time. And we definitely shouldn't write the average speed as v average, because that symbol is already taken. V average was a vector. If you take the vector sign off of it, it means the magnitude of the V average of the average velocity vector, and that's not what average speed means. So how would you calculate average speed? Well, you would look at the path and you would measure with a ruler exactly how long the path is, and then you would divide that by the amount of time it took for the object to go from the beginning to the end. Measuring with a ruler along the path is not something we've done yet, but that's the definition of it. And that's what average speed means. Okay, finally we get to acceleration. So why did it take so long to get to acceleration when we said that that's the one thing we need to know in order to move on to Newton's laws? Well, it's because they build on each other, right? The position was used to determine the velocity, and now the velocity is used to determine the acceleration. So let's just write down our definition. Average acceleration is a vector, and it was defined to be the change in velocity over some time interval divided by that time interval, delta t. So let's try and look at that graphically. I don't need to rewrite positions and find displacements anymore, because we learned that if I just pick out 2 points on the path, I can immediately write down the velocity vectors. Let's assume that the bird keeps the same speed, so the magnitude of these velocity vectors will be of equal length. So let's draw that. So let's say that the bird is going like this at this point. That's a vector which is tangent to the path and has some length. And then tangent to the path here is like this vector, and I'll try to make it have the same length. So it's like that. So if this is some initial time, then we can call this the v at t initial, and we can call this vector v at t final, like that. So we have a time interval between this point and this point. We have the initial velocity vector and the final velocity vector, and we can ask ourselves, what is the average acceleration? Remember, average acceleration and average velocity are over a time interval. So let's do it graphically, just like we did for the displacement. So the definition here is that the average acceleration is v final vector minus v initial vector over delta t. We weren't given any information about the time interval, not yet at least, but we do know that the time interval doesn't have any effect on the direction of the average acceleration. Remember, this vector points in the same direction as this vector. So let's just focus on delta v and calculate that. So delta v vector is equal to v final vector minus v initial vector, which again is v final vector plus the minus v initial vector. So let's find that. Where should we do that? Let's just do it here. So put a coordinate system down. Let's copy our 2 vectors. And then we have the first vector is the final vector. So we'll bring that down to our coordinate system. That's our v final. And we add to that not the initial vector, but minus the initial vector. So again, we take the initial vector and we turn it around. So it points along the same direction, but in the opposite direction. So this isn't the v initial, but it's the minus v initial. And I'm going to add that to my v final vector. And the result that we get, which goes from the beginning to the end, is called the delta v vector. So the delta v vector associated to this time interval, from that point to that point, points sort of up. And because of the definition of the average acceleration, because the average acceleration vector is equal to delta v divided by a number, we know that average acceleration points exactly the same way. So I could associate an acceleration here. I'm just going to put it near the middle of the interval. It really corresponds to the entire interval. I can draw the average acceleration vector as something like that. And just like before, when we didn't know the length of it, because we don't know the time, I don't know its length. Just like before, the accelerations live in sort of a different world. Their lengths can't be compared with like your length in meters, because they're measured in meters per second squared. But we see something useful here, which is that if you have an object that travels along a curve, it has velocities that point tangent to the curve at every point, and based on this definition, that means the acceleration points inward on the curve. We're going to spend an entire lecture or two talking about exactly that process. It's called circular motion, and this is often called a centripetal acceleration. We'll come to that later, but you can see it immediately just from our play with the definitions of the kinematic quantities. Instantaneous acceleration, I think I won't do any more calculation with that, but you can see how we do it. So we calculated the delta v like this. To get to the instantaneous, we need to take the limit as delta t gets smaller and smaller, and so as you bring this point closer and closer here, the velocity vectors will get closer and closer together, and you'll get some difference between them, which will be the acceleration at that moment in time. So let's do an example. This is sort of our first physics problem. So the question is, we have a scout troop that is practicing their skills of orientation, walking through the woods, using a map and a compass. They start at camp, wherever that is, walk due east for about 1 kilometer, then they walk 45 degrees north of west for almost 3 kilometers. And the question is, what is their direct route, the distance and direction, back to camp? So physics is a difficult subject, and one reason that people find it difficult is because you have to translate something in words into an equation. And for every one of the subjects that we cover this year, I'll try to show you how we do that. There should be sort of standard methods associated to that. But just knowing that there should be an equation that we can write down that will help us to solve this is sort of helpful to know that that's where we're headed. But usually before you get to that point, before you can write down exactly the equation that you want to solve, you should probably try and sketch something out so you can sort of see the problem. So let's do that. So I'm going to put a coordinate system down because I've done problems like this before, and I know that that's sort of a helpful thing. And I'm going to put camp at the origin of that coordinate system. So let's put this thing here. So our camp is the starting point, and it's going to be at the origin. Now let's show what is described in the problem. So it says that they walk east. So if this is a map, remember north, east, southwest, look like this. So if they walk east, then that means they walk directly along what I could call the x-axis here. So that means that they walk, say, let's say to here. Oops. They walk to this point here. So that's their first stop, and that's going to take them 1.2 kilometers. And then they're going to go almost 3 times that distance, but in a direction north of west. So what does that mean, north of west? Well, the west direction is backwards in the negative x direction. And when we say north of west, we mean an angle that takes an arc in the direction north. So we can take this to be our theta, which is 45 degrees, and it's going to be, they're going to be going then in this direction now. That's about 45 degrees. And they're going to go, well, if this is our distance, then they're going to go 1, 2, 3 of those, maybe out to here. So let's try and sketch that out. So maybe they'll get to this point here. Let's see. Oops. So, so what does that mean? How do we answer the question? Well, you can sort of see what they want to do now. They want to go from the point where they sit in the woods and go back to camp. So it's going to be something like along this direction. But now let's try and assign the quantities that we've already learned to this type of problem. So everything that's shown here is the movement in position space, going from one point in the xy plane to the other. And we could think about these as 2 or 3 displacement vectors. So they take one displacement vector that goes from camp to that first point, and we could call that delta r1, the first displacement vector. And then they go from that point to the northwest, and we could call that delta r2. We can put some of the information that we have here on the plot. So we know that delta r1 in magnitude is equal to 1.2 kilometers. And we know that delta r2 in magnitude is equal to 2.7 kilometers. And we want to try and get an equation out of it. Well, what they really want to do is they want to take a third displacement that takes them back to the origin, back to camp. So there's a delta r3 that's also on the picture here. Well, what is that picture? We know what that is. It looks just like a graphical addition. So we have a delta r total, which is equal to delta r1 plus delta r2 plus delta r3, right? This is graphical addition. And in fact, we know more than that because we can see exactly what delta r total is. If they arrive back here, then when you try to draw that resultant vector from the beginning to the end, well, the beginning is the end. So they end up right here, and it's a 0 vector. So we can write this equation that we found as delta r1 plus delta r2 plus delta r3 is equal to 0. What do we want to do in this problem? Well, we know what delta r1 is, we know what delta r2 is, they were given, but we don't know what delta r3 is. We want to find both components of the delta r3 vector. So we actually need 2 pieces of information, like an x and a y component of this vector, and yet we only have one equation. So is that bad? Are we not able to do that? 2 unknowns, 1 equation? Well, remember, it's not one equation, it's a vector equation, so it actually is 2 equations. So one way that we can solve this problem is we'll have 2 equations with 2 unknowns. So that's one way of solving a vector equation. Let me step back just for 1 second. Remember, our basic problem, which is going to haunt us perhaps throughout the entire course, is how do you take some question in English and make it into an equation? That's often the hardest part, and we just did it. So the rest of it is really just math. Now we're just going to do some math to try and answer what is this unknown quantity here. This is probably the most difficult part, trying to get to the equation that you want to solve with math. And it's a skill to develop it. One of the tools that you'll use is to try and make nice pictures, to try and label those pictures. Another tool is that you need to remember all the techniques that we have. So to recognize that moving from one place to another in space is what's called a displacement. And then trying to make equations out of it. That's another tool that we have. So, okay, so what do we do with a vector equation? And the answer to that is something that will help us not only in this segment of the course, but almost everywhere in the entire year of the course, because as I've mentioned before, all of our physical laws are written in terms of vector equations. So the answer is that there are two options. So let me write that down. So to solve a vector equation, there are two possible routes. So the first one is graphical, and the second is algebraic. So the graphical means using basically graphical addition of vectors, using the vector diagram that we've already found here. And then often it will involve some trigonometry or geometry in order to find the unknowns. Algebraic means that we use coordinates. Well, we use a coordinate system to give us components of the vector. So let's do both of those methods. So the first is the graphical method. And we want to use the picture that we have up here. So we already know that this picture represents this equation. So that much is true. And now we can try and use it by redrawing it. So we drew it as vectors first, but now let's draw it just as triangles. So here's one triangle, and that has our delta R1 vector on one side. Well, it's not a vector anymore, it's just a length. So I took the vector sign off. It has delta R2 on the other side, and then our unknown delta R3 over here. Is there anything else we know? There is. There's a theta there that we know. Remember, it was 45 degrees. And at this point, it might not be clear how to find the unknown side, delta R3. I think there are some techniques that you might know better than me, like laws of cosines or sines or something like that, that might help you here. But I basically always just use right angle trigonometry. So I'm going to make a right triangle trigonometry or geometry. I'm going to make a right triangle out of this by adding in another side. So that's a right angle now. Why is that useful? Well, I now can say that there's a side x and a side y, which I should be able to find using trigonometry, because I know what R2 is, I know what R1 is, and I know what theta is. So in this triangle, delta R2, y, and x, I can write, and theta, I can write sine of theta is equal to y over delta R2, and that means that y is equal to delta R2 sine of theta, and I can solve for that now. So delta R2, we had a number, it was 2.7 kilometers. Sine of theta was sine of 45 degrees. So now we can get a number for y. I think I won't calculate it right now. You can grab that number yourself. Then I can find the value of x. So cosine of theta is equal to x over delta R2, or x is equal to delta R2 cosine of theta. And you could plug in the numbers for that and find a number for x. So we have a number for x and a number for y. Well, how are we going to find the unknown? How are we going to find delta R3? Well, look at this. We have a right triangle. And if we knew what this side was, then we could just find it by Pythagorean theorem. So we could do that because we can find, I don't know, let's call this L. And we know that L is equal to x minus delta R1. And because I know what delta R1 is, it means I can find the value of L from the value of x that I had there. So now we can find delta R3, and again, I'm not going to go through that. Just in the interest of time, you can finish off that calculation. How do we figure out the direction that they want to go? Remember, we were asked to find both the distance that they'll need to travel and also the direction in which they go. Well, let's assign an angle to that. Let's call it, so let's say if this is the delta r3 vector, we could draw a direction south, and we could call this the phi angle. What is that? Well, it's a vector that now points this way from south. So that's east of south. So to find phi, so where is phi in this triangle? We have this is our phi. And we can find phi by saying, well, we know that tangent of phi from that triangle is equal to L over y. And that will allow us, remember L and y are now known, that will allow us to say it's equal to some degrees, and the direction that they want to travel with that vector is east of south. And that will be the answer for the direction. Okay, so that's the graphical method of solving this equation. Now let's do the algebraic. So the second method of solving a vector equation is algebraic. And our vector equation, our starting point was delta r1 plus delta r2 plus delta r3 as vectors is equal to 0. If we choose a coordinate system, which we already had, recall it looked like this, then we can write that as two scalar equations. So there's an x equation and there's a y equation. The x equation is 0 is equal to delta r1x plus delta r2x plus delta r3x. And the y equation is 0 is equal to delta r1y plus delta r2y plus delta r3y. And remember, we know everything about r1 and r2, so we're going to be able to find those two, and that means you'll be able to solve for delta r3x. So let's take them one at a time and look at what they are. Well, delta r1x, let's go back and look at it. Delta r1 points exactly in the x direction, so it is only in the x direction. So maybe we should just write that out here. Delta r1 is equal to something in the x direction, comma 0, and let's just call it delta r1 magnitude. We know that that's 1.3 kilometers or 1.2 kilometers, but let's give it a variable name instead. And delta r2, well, that one's a little bit more difficult. Let's put it on our coordinate system. It's a vector that points at 45 degrees because we had this angle here, theta, given to us as 45 degrees. And we want to find its components. Well, this is going to be delta r2y, and this is going to be delta r2x. And we can find those values. So let's draw ourselves a little triangle, x, y, theta. We see that cosine of theta is equal to x over, and what is the hypotenuse? Well, it is just delta r2. That's the number that we know. That's the 2.7 kilometers. So x is equal to delta r2 cosine theta. And if you do the other one, then it's going to be y is equal to delta r2 sine theta. Those are the positive sides of a right triangle, but they're not necessarily the components because this tick mark here is on the negative x-axis. So if I'm going to write out the components, they are going to be minus what I found for x, which is delta r2 cosine theta. And then the y component here is a positive number, so that's going to be positive delta r2 sine theta. Okay, so let's try and solve our problem now. So let's take the x equation first. So we have 0 is equal to r1x. Well, that is this number. That's delta r1. The delta r2x is this number. So if we add that, it's going to be minus delta r2 cosine theta. And delta r3x is an unknown. So we leave it as an unknown. So these numbers, just keeping track of what is known, those are all known because they're just numbers that were given to us, and this is the unknown. So you can see that you can solve immediately for delta r3x now. By the way, I recommend that you try to keep everything in variables until the very end. So when does that happen in this case? Well, it happens once you rearrange this equation to say delta r3x is equal to, and then I guess it would be delta r2 cosine theta minus delta r1. So you do the algebra to rearrange, and now you can plug this into your calculator. And that will give you a number for delta r3x. And of course, I won't do it, but you can do the same thing for the y equation, taking the components that we found here, plugging them into this equation, and getting a number. And then once you have delta r3 vector, which is delta r3x, delta r3y, you can get magnitude by taking the square root of the sum of the squares. And you can get direction by, I would draw the vector out and find one of the angles with a tangent. And you can finish that off on your own. So the last section of this lecture gets at how we can analyze position, velocity, and acceleration in one dimension, which we're going to spend quite a bit of time doing, not immediately, but in a couple of lectures. So I wanted to present vectors first, but we're often only going to look at the components along one direction, which reduces things to a one-dimensional motion case. And I want to show you why we're able to do that first. So let's just look at average velocity. Remember the definition of average velocity? Do you remember? It is the displacement divided by the time interval, delta r divided by delta t. And if we choose some coordinate system, then that means that it's going to be equal to delta x over delta t, comma delta y over delta t, comma delta z over delta t. Let's just leave it for 2 dimensions for now. And because that's a vector equation, what we mean by this is that the x's and the y's are completely separate. So I could just write it as an x equation and a y equation. V average x is equal to delta x over delta t, and V average y is delta y over delta t. So this basic principle of vectors, that you can separate out the x's and the y's, and they're completely independent equations, is extremely helpful. So let me just show you a quick example why that's helpful. Well, imagine that you have a river here, and the river is flowing with some velocity. So V river, it's flowing that way. And then you yourself come to the river and you want to swim across. And so you dive in and you start swimming, and you're going to have some velocity that you can swim with respect to the water that maybe you measured in a pool the other day. And that's your swimming velocity. Well, as we talked about in the first lecture, and as we'll talk much more in the next lecture, the actual velocity vector that you take will be the sum of those two. That's the way that you'll actually flow with respect to the Earth. So the actual resultant vector will look something like this. So this is the way that you go. That's your total velocity vector. So you point yourself directly across the river and start swimming to the other shore. Maybe your friend is sitting over there. But the way that you go is actually down the river, because the river is carrying you that way. Well, how long is it going to take to get to the other shore? You're not going to end up where your friend is. You're going to end up down here. But how long is it going to take to go that distance. Well, amazingly, you don't really need to worry about the fact that you're going down the river in order to figure out how much time it is, because you can separate out these equations. If we say that across the river is the y direction and down the river is, say, the minus x direction, we only need to look at the y equation, v average y is equal to delta y over delta t, to figure out the delta t. So delta t is just equal to delta y over v average y, or in this case, oops, the delta y is just the distance across, right? The difference along the y-axis of your position, that's just d. And the v average y, well, that's the y component of this vector is going to be our v average vector. It's the y component of that. Well, that's just v swim. So it's just the speed with which you can swim as you're pointing yourself directly across. So we can completely ignore the river in order to answer the question of how long it takes to get across. And that's because the x and the y components of these vectors are completely independent. So as I say here, horizontal motion can be described completely separately from vertical motion, or in the way that I just did it, vice versa. Everything's completely independent. So we're going to look at, in just a moment, the graphical relationship between position, velocity, and acceleration. And we're going to look at it in one dimension, so just like the x direction. So that will be comparing x, and we're going to look at it versus time. And the velocity in that direction, so v sub x versus time, and then the acceleration in that direction, so ax versus time. So what does that represent when we start to draw x versus time or vx versus time? Well, it could mean that you just have an object moving in a straight line. So maybe you have, a road, and you have a car on that road, and that car is moving in this direction, and then we could sort of measure out its progress along the x-axis. So it doesn't move in the y direction at all, so it's just moving in the x direction, so we only need to keep track of the x value as the car moves along, and then because of the way the equations work, we only need to keep track of the vx value and the ax value. That's one possibility. But because of the fact that these equations separate out completely, it's not the only possibility. We could just look at the x part of the motion. So in fact, you could look at, for example, if you throw a book off of a table, so here's our book, and it's going to take some trajectory that looks like this, well, we could just be talking about, for example, the y position of the book over time without even thinking about the x position. So, or I guess since I said x here, we could be talking about the x position of the book over time without considering what's happening in the vertical direction. So these graphs could be explaining one component of the motion, and then you could write down completely separate graphs, y versus t, vy versus t, ay versus t, to describe the other part of the motion. So let's see what that looks like. So let's try and understand what our kinematic quantities represent on these graphs. Now notice I'm no longer drawing a coordinate system, I'm drawing x, the x position, so the position of an object on an x-axis, versus time here, as measured in seconds. And this graph is meant to represent some object. So what does this graph mean? You're going to want to spend some time trying to understand what a particular curve means on a graph. Well, this one, if you notice, in the early times, the x value hardly changes at all. So the object isn't really moving at this point. And then very slowly, it starts to increase its x position. So maybe this is like a car that's at a stoplight, and then slowly it's increasing its x position. And then you can see at a certain time interval later, it's increasing its x position by a lot more. So this is like a car speeding up. So let's write that. Car speeding up. Now, what is average velocity? Well, remember, average velocity corresponded to a time interval. So you have some t initial and some t final. And average velocity was defined to be as a vector, delta r over delta t, but in its x component, the average x was just delta x over delta t. And delta x over delta t here is just the slope, right? This is delta x, and this is delta t. So v average is going to be the slope of a line that connects the 2 points. So the answer here is slope of a line connecting the 2 points. What I mean by 2 points are the points at the initial moment and initial position of the interval and the final moment and final position of the interval. That's how we represent average velocity on a graph. How do we represent velocity? Well, velocity is when you take these 2 points and bring them closer and closer together. So we could look, for example, at what is the velocity at this point here, and that's going to be represented by a line that doesn't connect 2 points, but is the tangent line to the curve. So v sub x is the slope of the tangent line. And you can see that that's just the limit of the slope of a line that connects 2 points. As you bring the 2 points closer together, then your line becomes more and more tangent, as we saw before when we were talking about displacement, and therefore the slope of the tangent line is how you get the velocity at a given moment in time. How about for the v versus t graph? Well, first of all, what is this? We have some positive velocity, and then that positive velocity gets smaller and smaller. So that could be a car that's coming to a stoplight. Car coming to a stop. So the velocity is getting smaller and smaller. Eventually, it looks like the velocity will head to 0, and then the car will be stopped. Well, what happens if we connect points here? So if we have some t initial and t final, what's the slope in that case? So if we connect those points, well, the slope here is delta Vx over delta t. And what is delta Vx over delta t? Well, that's exactly what we mean by the average acceleration, because average acceleration is delta v over delta t, and average acceleration in the x direction is delta Vx over delta t. So the slope of a velocity versus time graph is the acceleration. So that's the connection between these graphs. You draw position versus time, look at the slope and get the velocity, draw velocity versus time and look at the slope and get acceleration. And these were two different objects, right? A car speeding up versus a car coming to a stop. But now we can draw the sequence of position, velocity, and acceleration for the same object. So let's use our bird as an example. So I'm going to draw now the position of the bird, and let's just, because I think it's easiest to see, let's draw the y position of the bird. So remember, we can draw a coordinate system here, x and y, and the y position is just where the bird is at the certain moment in time. And if the bird sort of has a constant horizontal velocity, then the y graph versus time will look very much like the y graph versus x here. It doesn't have to be exactly the same, right? If the bird somehow stopped in the middle of the air, then the y would get a flat part to the curve. But if we assume the bird just sort of moves constantly across, then this would be something like the graph of the position versus time. So the vertical position of the bird versus time. Now, let's draw Vy versus time, so the velocity versus time. So we know what it is. We know that Vy is equal to delta y over delta t, meaning at any moment in time, the number that you plot for v is the slope of the y graph. Now, that might be sort of hard to do. I mean, it's definitely hard to do in terms of numbers because we don't have any numbers on our graph here. But qualitatively, we can do it. And there's a trick that you use. So the trick is to find the points where it's easiest to actually find the slope. And that is the places where the slope is equal to 0. So if we look at each of these points here, you see that if you draw a tangent line, the slope is 0. And that means that Vy, the velocity in the y direction, is 0 at those moments in time. So we can just drop down, and we know that this moment will have a velocity of 0. And this moment will have a velocity of 0. And this moment, 0 velocity. And finally, this moment, 0 velocity. So I haven't drawn a velocity graph yet, but I know the places where it goes through 0. And in a lot of interesting examples, it's nice just to see what it looks like. And so we can do that. So how do we connect the graph that goes through these points? Well, the graph is either going to be above 0 velocity or below. And the way that we can tell is we can look here and see that the slope is positive. So everywhere before this line where it's 0, the slope is positive. And here, the slope, which remember is delta y over delta t, which is Vy, is negative. So when we plot the values of Vy, it's going to look something like this. Positive, negative, positive, negative, positive. Maybe my last one is a little bit weird. I don't think it goes up so abruptly there, but you get the idea. So the velocity graph is going to look something like that. The velocity in the y direction. Velocity in x, remember we said was going to be something, we agreed that Vx was going to be fairly constant, and it would basically just look like that. It's always going the positive x direction, and it doesn't change very much. That's the reason that our y versus t graph looks like our y versus x graph. Now last step, what is ay? So the acceleration is the change in the velocity graph over time, meaning it's the slope of the velocity graph. Well, we do exactly the same thing. We find the points where the velocity has a slope of 0, and we call those points points of 0 acceleration. So I know that the acceleration goes to 0 at these points, maybe somewhere here. And then again, we look at the slope. Well, you can see the slope is negative in between these 2 points. So that means I need to draw a negative curve here. The slope is positive here. So I draw a positive curve here. And then it becomes negative and then positive. And it's positive there. So this is a very qualitative sketch, but it does contain some information. It does tell us sort of when, just by looking at this, we can see approximately where the acceleration is equal to 0, for example, and that would appear right here on the curve which is somewhere around here. The acceleration in the y direction goes to 0 after the bird takes this upward arc and before it takes this downward arc. It turns out that these points where it's making the arc are the points which have the largest value in the acceleration. So there's a lot of information contained in there. And this is a technique that you'll use in the lab and that we'll do in some problems. So that